right, so in this screencast, you're going to learn all about kind of the basics of acids and bases, as well as conjugate acids, conjugate bases. So our essential question is, what is the difference between an acid and a conjugate acid? I could have also asked, what's the difference between a base and a conjugate base? Same thing. So we're going to start off with some of the properties of acids and bases. Acids taste sour. Most of your candies, like sour candies, have citric acid in them or some or other type of acid. That's what gives them the sour taste. Most acids will dissolve some metals, cause plant dye to change color. So that is why we see like pH paper working. Bases tend to taste bitter. They are slippery when you feel them, so think soap or laundry detergent. Most of them are corrosive, so they will eat away at things, as well as poisonous. Bases don't taste good to you because most of them are poisonous, and that's your kind of evolutionary way of not eating that, is for it to taste bitter and not appetizing. So there's three theories of acids and bases. As far as like what's an acid and what is a base, there's the Arrhenius, the Lewis, and the Bronsted-Lowry. So we're going to talk about all three of these and kind of what their differences are. So for Arrhenius, the definition of an Arrhenius acid is a substance when it's dissolved in water dissociates to produce hydrogen ions. Makes sense. We associate hydrogen with acids. We associate, high hydrogen concentrations with a low pH and being an acidic solution. So the hydrogen ion, also called a proton, because it is just one proton, that hydrogen ion. So HCl is an acid because in water, in an aqueous solution, the hydrogen ion and the chloride ion dissociate. And so because hydrogen is released, by definition, that's an acid. So an Arrhenius base is a substance when dissolved in water dissociates to produce hydroxide ions. Okay, fair enough. So if we have sodium hydroxide or any other hydroxide compound, when we put it in water, it will dissociate into sodium and hydroxide. So that is why that would be considered an Arrhenius base. The problem is, where do things that don't have hydroxide fit in at? So like ammonia. Ammonia is a base. Ammonia is a pretty strong base. But ammonia, when it dissociates, it does not form OH. So by Arrhenius' definition, it cannot be a base. So that's where we now look at the Lewis acid, Lewis base definition. So for a Lewis acid, it can accept electrons, meaning it is something that is going to be an electron pair acceptor. It's going to take electrons from something else, whereas a Lewis base is going to donate electrons. So it's going to give them away. Okay, well, let's take that definition of the Lewis acid, Lewis base, and build on it with the Bronsted-Lowry theory, which is really what we use for the most part today. We think about an acid for Bronsted-Lowry is going to be a proton or a hydrogen donor, and then the base is going to be a proton or a hydrogen acceptor. In this case, as long as we've got hydrogen, which is by definition what an acid is for all of them, the bases can be a base without having hydroxide to it. So it's going to be a hydrogen acceptor. So let's look at this example where I have hydrochloric acid plus water yields the chloride ion and H3O. So what donated the proton? Well, if we look at this, H is bonded to Cl over here. And then on this side of the equation, chlorine is by itself. I have H2O on the reactant side, and then on this side I have H3O. So what happened here? This, the hydrochloric acid, lost that H, and this, the H2O, gained it. So what donated the proton? The HCl. What lost it? And then what accepted the proton? H2O. So the proton donator is our acid, the proton acceptor is our base. And if you look at what they become on the other side, H2O becomes H3O. So of course it gained one, so that makes it the base, it's the acceptor. And the hydrochloric acid lost one. So it's what did the donating, it's what's the acid. So the cool thing is, let's look at this one right here. NH3 plus H2O yields NH4 plus OH. So NH3 starts out here as NH3, and it becomes NH4 on the other side, so it gained a proton. H2O lost a proton and just became OH on this side. So the NH3, because it gains a proton, it's the base. And the H2O in this case is acting as an acid. So did the NH3 donate or accept a proton? It accepted one. Is it an acid or a base? So because it accepted it, that makes it a base. What is water in this reaction? Water is actually an acid. So water possesses both acid and base properties, as you guys have just seen. It's called amphiprotic. It's a substance that possesses both acid and base properties. It just depends on what it's reacting with. So the hydrogen can split off, that's the acid part, and the OH could split off, that's the base part. So distilled water, what makes it a pH of 7 is it has equal parts of the hydrogen and equal parts of the hydroxide, making it neutral. But it has both properties. So a little bit about what are these conjugate acid and conjugate bases. So the acid-base reaction can be written in the general form, which we're going to have the acid is going to have hydrogen bonded to it. And what makes it an acid is it loses that hydrogen, and what makes this the base is it gains it. So the acid is going to lose the hydrogen and the base is going to gain it. So because most reactions are reversible, remember, if something is an acid and a base on one side, then it's going to be an acid and a base on the other side. So you got to figure out what the acid and the base is on the other side. And that's what we call the conjugate acid, conjugate base. So we call them acid and base on the reactant side. We call them conjugate acid, conjugate base on the product side. Because in the reverse reaction, this would be the acid and base, and this would be what they would form. So let's do some analysis. So if this is my acid, what it becomes on the other side is something that has lost a hydrogen. So that would make it my conjugate base. So right here, if this is my acid, on this side, it would become a base. This is my base on the reactant side. It gains a hydrogen. So on this side of the equation, it would be the acid. So we would call this the regular acid and base, and we would call this the conjugate base and the conjugate acid. So the conjugate acid is what the base becomes. So BH is the conjugate acid of the base B. It's what it becomes on the other side. And the conjugate base is what the acid becomes. So the acid, when it loses its hydrogen, becomes this base. So all you have to do is really just pair up with what it becomes. So like in this example, NH3 becomes NH4, so it gains a hydrogen. So that means it's a base on this side, it's a conjugate acid on this side. The H2O becomes O, so it actually loses hydrogen, so that's my acid on this side, that's my conjugate base on this side. So go ahead and try these, we'll work these out in class, but go ahead and try these practice problems. And then we're going to talk a little bit about acid and base strength, because not all acids and bases are equal in terms of how strong they are. Acid and base strength is based on their degree of dissociation. What that means is how much they break apart. Strong acids and strong bases, their reaction with water is virtually 100%. So like in this case right here, you notice we only have the arrow going this direction. There is no reverse reaction here. What makes this a strong acid is when it reacts with water, you will form almost 100% products. And so you will end up with a whole bunch of hydrogen in there, making it a very low pH. What makes this a strong base? Notice there is no reverse reaction here. You form basically 100% products. So you will end up with a whole bunch of hydroxide, making that have a high pH. So strong acids and strong bases, when we say they dissociate, that just means they go 100% to products. The reaction is complete. All of the reactants become products. At the end of the reaction, you have no reactions left. Reaction is completely gone to products, and it's generally shown as a non-reversible reaction, which is what I just showed you. So here's some examples of strong acids and strong bases that are going to completely go to products. So hydrochloric acid, hydrobromic, hydroiodic, those are our binary acids. Nitric acid, sulfuric acid, perchloric acid, these acids are very strong, and when you add them to water, they will completely dissociate into the hydronium ion, or into the hydrogen ion. Our strong bases are pretty much anything with hydroxide, so sodium hydroxide, potassium hydroxide, barium hydroxide. So when you add these to water, they go basically 100% to products, making them very strong. But all the metal hydroxides, so whenever you see a metal bonded to a hydroxide ion, that's going to be a strong base. Now there are weak acids and weak bases, and what makes them weak is only a small percent dissociates. So you see how only a small amount becomes the product, so we show these as reversible. So in this case, we have acetic acid, which is vinegar. That's the formula for vinegar, reacting with water. And some of it is forming this conjugate compound, but then some of it is also forming the acid part. So here's my base and here's my acid part. And some of it's dissociating to the hydrogen ion or the hydronium ion, but not all of it, because it is reversible. The same thing with carbonic acid. This is what's happening inside of your cells. Why your body has to get rid of the carbon dioxide it produces. So you've got carbonic acid forming, and you've got some of the hydronium ion forming, but notice that the reaction goes in the reverse. So these are what we would call weak acids or weak bases. The reactions are shown as reversible. They do not go completely to products, and that's the difference. And here's some examples of weak bases. Ammonia breaking down. Ammonia is pretty strong, but it's not as strong as a hydroxide, but ammonia breaking down. We've got pyridine breaking down, which is just another compound that's found in your body. Aniline, another compound that's found in your body also, breaking down. But you'll notice that, yes, they do produce the hydronium ion, or sorry, the hydroxide ion, making them bases, but these reactions are reversible, so it's not 100% going to products. So here's a table that's going to show you kind of the difference between the acids and the bases. So if something, here's acid strength. So these guys are strong, these guys are weak, and then down at the bottom we have negligible because they don't really dissociate that much at all. And you'll notice that if something is a strong acid, then its conjugate base is actually really weak. So the strong acids produce conjugate bases that are pretty weak. But the weak acids down here produce pretty strong conjugate bases. So by using this table, you can actually, predict what the acid part is and what the base part is, but also what their strength is going to be. So again, if something is a strong acid, it produces a pretty weak conjugate base. But if something is a weak acid, it produces a pretty strong conjugate base. So which acid is stronger, HF or HCN? If you just look at the chart, here's HF and here's HCN, so HF is higher. That means it's stronger. But which base is stronger? Which of its conjugate pairs is stronger? You can compare that between HF and HCN. So CN is down here, making it a stronger base, a stronger conjugate base than the F is. And which base is stronger, CN or H2O? CN is right here. And H2O is up here, so CN is actually stronger. You notice it goes the opposite direction. So that concludes our discussion about conjugate acids, conjugate bases. Work through those practice problems, and we will review them in class.